Hi, this is a discussion on the conversion of scientific papers into minimally viable assays, and it's really solving that gap between what's done in the laboratory and how to get these kind of assays into the hands of end users, specifically end users who are not necessarily electrochemists. So in the literature, for example, you can find a strong paper, and this one's on the voltammetry of rhodamine. And it's also done on what's called a screen printed carbon electrode. So there's a couple of things that are super interesting about this paper. It's done on a screen printed carbon electrode, so it does have features that allow it to become a assay that could be rolled out beyond the laboratory. And in this case, they've used voltammetry, and there's lots of types of voltammetry: cyclovoltammetry, differential pulse voltammetry, square wave voltammetry. Now, what we're going to say in this video is that you can go from voltammetry in a scientific paper like this to sort of something on a smartphone where you actually deliver a piece of information, for example 10 micrograms per milliliter. And so what we'll talk about in the rest of this video is the technology necessary to go from literature to useful information, let's say, that somebody can receive on their smart device. So let me describe that process, let's say. So if you have the paper, then often there will be also in that paper published, as I said earlier on, the voltammetry. The voltammetry is often feature rich. So voltammetry often has a qualitative content. These features are indicative of the molecule of interest, and there's also a quantitative feature that the peak heights that we get in this voltammetry are also indicative of the concentration. Now, here we have the voltammetry of a organic molecule. It's very distinctive. It has, for example, 3 peaks. One of the peaks actually doesn't appear on the first scan, it only appears on the second scan. I really want to contrast that now with a much simpler voltammogram. Here we just have what we call an oxidation and reduction peak. Now, the voltammetry itself is not interesting. It just illustrates a point, which is that in some applications, the molecule that you're trying to analyze, it could be a molecule using tracing, or it could be a molecule that's part of food quality. Whichever, these molecules can sometimes be in quite high concentration. That does actually help this kind of work. But that voltammetry that we're looking at here is, rather than a voltammetry, you can consider it really a fingerprint. So we have a fingerprint for one of the molecules, and it was easy to argue in this example that that's very different from the voltammetry of the other molecule. So to go back to the original point, what we're talking about in this video is the conversion of a scientific paper into a minimally viable assay. And we're really following the principles from Silicon Valley about minimally viable product, the minimum feature set to make a assay useful for somebody outside of a laboratory setting, or a user who might be technical but maybe, for example, a non-electrochemist. So let me dive a little bit more into this now and say this particular paper, and this, but in more generally, at Zimmer & Peacock we produce a range of screen printed electrodes. This one is our hypervalue electrode. I like it because of the quality and also the cost, that it's less than 50 cents each, which, depending on the exchange rate, can be sort of 40 US dollar cents, 40 euro cents, or about 40p if we're talking about Great British Pound. So there's the screen printed electrodes. We need something that we call it the OmniSense. It's really a potentiostat, but it's not a potentiostat of the sort of normal ilk, and I'll explain what I mean by that. And we also need a cloud database. So this is Julie. So Zimmer & Peacock, I think we have the world's only commercially available database, cloud database, for the uploading and analysis of electrochemical data. And this is critical to what I'm about to describe. So what we are expecting is that the sensor will, or the electrode in this point, the screen printed carbon electrode, goes into the potentiostat, and then the sample obviously goes on what we call the proximal end of the screen printed electrode. Now, at which point that sample, for example, could contain the molecule that was in the original paper. So for example, in this case, rhodamine B. Now that omnisense meter, or it's really also a potentiostat, it does not know what to do, but we can train it what to do because we have app development. And so the app development, it's easier to tell the app what to do because obviously the original conditions for gaining that voltammogram were in the original paper. So it's not so hard to tell the app what to do, and the app is actually only in Bluetooth connection with the meter itself. So the meter can take the screen printed electrode, and we encourage everyone onto our hypervalue carbon electrode because of the quality, but also because it fits into this workflow as well. So screen printed electrode into the meter makes Bluetooth connection with an Android. We like Android because there's a lower cost, easier development path when making Android rather than iOS apps. The app, we know what the app needs to do because it's in the original paper, and then the app will tell the meter what to do, and the meter then importantly gives the raw data back to the app, at which point now the app has an upload button. So now this upload button uploads it to Julie. So Julie, if you Google Julie and a Zimmer and Peacock, you will find this database online. And Julie, if you go into it, it actually can receive electrochemical data. And when I say receive electrochemical data, it can receive data from ZEP's proprietary potentiostats, for example. It can also receive data from other people's like CH Instruments, and also receive data from Autolab, for example, and also data from PalmSense. So we can get the data into the cloud, at which point now Julie really kicks in, because Julie is able to confirm that that voltammogram has a feature set that's indicative of the molecule of interest. So we're able to analyze this using Julie, and first of all, let's say validate that it is the molecule of interest. So that's a sort of that's the qualification part. And then Julie can also then do things like baseline subtraction to allow us to actually analyze the peak height and do sort of mathematical manipulation on the data so that we can extract essentially a signal from the entire spectrum. For example, if we're going to call it a spectrum, we'll call it a voltammogram. So we can do what we call feature identification, and we can then go on. And again, this is great because in the original papers, you'll often find a calibration. Now the calibrations, this becomes much quicker when people are actually on these hypervalue screen printed carbon electrodes, because the calibration that they've done in the research phase is actually applicable to this, let's say, this development commercialization phase. So we have that's because in this particular case, the signal is proportional to the area of electrode. So it's important to be on an electrode that you're also going to potentially commercialize on, let's say. So anyway, from the literature, you can often get a calibration curve. So for example, here, we can see that it's actually peak height is proportional to the concentration. And so Julie can know this calibration curve. We can train her essentially. And then it means that the raw data goes to Julie. Julie validates that this is the molecule of interest. Having passed that test, then Julie can then go into calibration routine where we can look at the peak height, for example, having maybe done a baseline correction. We can look at the concentration, and now this is the important bit, actually deliver a number that is meaningful to the non-electrochemist. And so what we've now described then is the idea that in fact you can have a scientific paper with voltammetry in it, but using the ZEP screen printed electrodes, the OmniSense and Julie, we can then quickly go from a voltammetry, for example, in a scientific paper, to a meaningful number which we can display, for example, in the cloud, and sort of say 10 micrograms per milliliter. Now, for a real user, then we can actually not display the voltammetry, not display the calibration routines, actually just allow them to run the app, upload the data, The data then goes through essentially two filters. One of them is a validation that is the molecule is there, and then there's a quantification to actually turn that into a meaningful number. And it's really an acceleration of the ability to take scientific papers or laboratory processes and actually turn it into a what I would call a minimally viable assay on a MVP, a minimally viable product. So if you have any questions about this, don't hesitate to reach out to us at Zimmer Peacock. Okay, thanks very much.